G'day and welcome. Today's video is part 2 in the quest to eliminate the fuel surge in my BRZ. Details are next. I'm Mark Louth from Black Dog Motorsport, and if you or someone you know has the black dog chasing them, there are some links in the description which you may find useful. At the end of part 1, we had a test fixture that we had manufactured ready for installation between the OEM fuel pump wiring and the fuel pump itself. If you haven't seen part 1, there is a link in the description, or you can click on the card in the top corner of the screen. For those of you who haven't seen part 1, I'll quickly catch you up. The Toyota 86 and the Subaru BRZ are great cars, but they're not perfect, and one of the few issues that they do have, and for me the most irritating, is their propensity to starve themselves of fuel during heavy cornering, especially when turning left. Now, the fact that you are watching this would tend to indicate that you already knew that, but just in case you didn't, that's the issue we are trying to fix. There are many methods and ideas as to the best way to achieve this, and you could argue one way is better than another if you wish. But fitting a second fuel pump is the method I have chosen to explore. Now, I have no idea at this point if it will work, as I hope, but nothing ventured, nothing gained. As I stated in part 1, in order to design a suitable wiring system to operate the second pump without upsetting the engine management system, I need to know exactly what is happening in the system when the pump is operating, and that is the reason for the test fixture. The first step in the procedure is to gain access to the pump wiring, and you would think the connector would be directly underneath the wiring grommet, but of course it's not. So we'll have to remove the whole access panel. Now, this is not hard under normal circumstances, but when you have no access from the rear due to the half cage, and both the seats are fixed and not adjustable, and you have to do it one-handed while filming, it's a bit of a drama, so please excuse the poor cinematography while I get this done. Once I have access, I can install the test fixture between the connector on the pump and the OEM wiring harness as shown in these images, paying particular attention to correct wire placement and polarity. Next is to install the testing equipment. I am connecting 2 multimeters and an oscilloscope to the test fixture so I can find out the voltage the system is running on, the current the pump draws, and whether the power supplied to the pump is direct current or pulse wave modulated via a square wave. I'm pretty sure I know the answer to these questions before I even start, especially the last one, but knowing for sure as opposed to guessing is always the better option. This first sequence is filmed on the phone and as a result isn't great, but hey, sue me, and it shows the general arrangement of the test fixture in relation to the physical location of the pump, etc., and it also worth noting the oscilloscope is not connected as yet. The meter on the left is measuring the voltage and the meter on the right is measuring the current flow. Okay, I've charged the battery on the good camera and hooked up the oscilloscope. I've then run the car again and taken notes of the measurements. Okay, so what are the measurements and what do they tell us? Looking at the oscilloscope, we can see that, as I suspected, the power being supplied to the pump is direct current and not a square wave, indicating that the pump is not pulse wave modulated. Looking at the screen, you could be forgiven for thinking the power is anything but direct in nature due to the undulations. However, if you look at the lower left corner of the screen, you can see the amplitude scale is set to only 500 millivolts per division, and in the lower middle of the screen it shows that the time base, or the time interval between samples, is set to only 5 microseconds. In other words, what we are looking at here is a super close-up of the power being supplied to the pumps. and it is indicative of what direct current looks like when it is powering an inductive load like an electric motor. This snapshot shows the measurements directly after the engine has been started and shows the power being supplied to the pump is 12.71 volts at a current of 4.71 amps. And interestingly, the oscilloscope shows a lower level of noise than on the previous slide, the reason for which I know not. Up until this point, the measurements have been about what I expected until this happened. As you can see, the ECU has dropped the supplied voltage from 12 volts to 8 volts, give or take, with a corresponding drop in current from 5 amps to about 3 amps, and the supplied voltage has got a lot noisier, and this frankly is a bit of an issue. Why is it an issue? Well, put simply, I don't know why the ECU is doing that. I mean, I could speculate with a reasonable chance of coming up with the correct answer, but as I said before, I would rather know as opposed to guess. More importantly, if my twin fuel pump control module doesn't do the same, what is the result for the operation of the engine? And will the ECU note the lack of change in the associated pump volume or pressure? And if it does notice it, will it throw a fault code? And the answer to all of that, ladies and gentlemen, is I have no idea. And that kind of makes it hard to design a suitable control module. So, leaving the unknowns aside for now, let's focus on what we do know. And that is, the pump is being supplied with 12 volts at 5 amps, give or take, on initial startup. And then after a short period of time, it then drops to around 8 volts at 3 amps. Changes in engine RPM do not seem to have a significant effect on the amount of power the ECU supplies to the pump, although there is an increase in line with an increase in RPM. Taking into account though, the engine was unloaded when the measurements were being taken, and owing to the fact that I don't own a dyno, I can't really test the car under load. Well, not on my own, at any rate. Now that we know the voltage and the current draw, we can calculate how much power the pump draws by using the power formula, which states that power is equal to the supplied voltage multiplied by the current drawn, and the answer is given in watts. So, using our measured data, we can see that 12 volts multiplied by 5 amps will give a power consumption of 60 watts, and boys and girls, that is a lot. And it is for that reason that I do not want to just simply tap into the existing wiring and branch it off to the second pump. Even if doing so did not cause the engine management system to throw a fault code, it would result in a current draw of 10 amps and power consumption of a whopping 120 watts. And while I don't know this for certain, I would humbly suggest that the existing wiring would not like that very much at all. And that's assuming that the pump does not draw a higher current than that when the engine is under load, which it very well may. Murphy's Law of Combat states that even the best laid battle plan does not survive contact with the enemy, and similarly my U-Butte idea for a twin fuel pump control module has not survived contact with the reality of what is going on in the system, which means I have to well and truly go back to the drawing board. The end result of that is I'm going to have to end this video here until I get a bit smarter and come up with a solution. Now, I would advise against holding your breath for that, as it may be detrimental to your health. Now, assuming I do work it out and you would like to see what I come up with, please consider subscribing as it is free. And as always, thanks for watching, and I'll see you in the next one. Bye for now.